Imagine yourself riding on a bicycle at a constant velocity, and you're chewing a piece of gum. Sometime along the ride, you spit the gum vertically straight up, and no matter how fast you're riding your bike or how slow you're riding your bike, the bubble gum will fall into your mouth again. And the reason why this works is due to gravity and inertia. All right. With regards to inertia, both you and the bicycle share the same horizontal velocity. Before you spat the gum and after the gum has returned back to you, the horizontal velocity remains the same. The only thing that is different is that the bubble gum had a difference in its Vy, all right, its vertical velocity, where initially it was traveling upwards and eventually was coming down. But throughout the entire journey, your Vx remained constant. All right, so that's one thing to keep in mind in these projectile problems. Your Vx is always constant. We're not worrying about air friction in these problems. We're also assuming that you're doing this experiment on the same planet. So if you're doing it on Earth, we assume that your AY is equal to negative 9.81. And lastly, whatever time it takes for it to go up and down is the same amount of time that it takes for an object to travel all the way across. So your time is the same in both dimensions. So you can generally categorize projectile problems into two outcomes, right? Either A, it hits the ground and the activity is over, or B, it hits a wall and the activity is over. So let's go through case A, it hits the ground. Now you could either start from a higher elevation and eventually it hits the ground. Okay, so you could have problems that look like this, or you could have the one where you might be in a ditch. All right, so you're in a ditch down below, and luckily when you shoot it up, it eventually hits up above. So it didn't hit the wall of, I guess, the cave or the ditch that you're in. Okay, so that's the hit at the ground example. In these cases over here, you want to solve for your y dimension first. All right, so generally you'd start off using a formula that looks like this. Delta dy is equal to vi delta t plus 1/2 a delta t squared. Solve for time. And after you solve for time, whatever time it takes for it to go up and back down is exactly the time it takes for it to travel horizontally. So you could solve for your dx, the horizontal range, by multiplying that constant horizontal velocity by the time that you calculated earlier. The second scenario is one where you launch an object and it hits a wall. So you could be at ground level and you shoot it and it hits the wall, or it could be a case where there are examples where you're in another building and you're shooting it, and the outcome could be one of two. Either it hits the wall and be higher from where you started at, or you're not launching it fast enough and it hits at a lower part of the wall. Okay, in these cases over here, you probably already know your muzzle velocity, so you could solve for your Vx component. And as you know your Vx component, and you probably know the distance between these two buildings, that's already a known given, then you'd start off with this formula first. Dx is equal to Vx delta t. Solve for time, and then you can use most likely this formula next. Delta dy is equal to Vi delta t plus 1/2 a delta t squared. Sub the time in, and then you'll get your delta dy. Keeping in mind that your delta dy does not tell you your position, it just tells you your displacement. All right, so the difference in elevation from where you started to where it is at the end. All right, so your grade 11 problems are one of these two scenarios, and that's it. As for grade 12, we like to deal with a lot more challenging problems where you don't know all the details in either dimension, and that's why you need to create two equations and then solve them together afterwards. Here's an excellent example of a grade 12 projectile problem. Baseball player makes contact with the ball travels at this distance and at that height. So if you need me to draw a little picture, sure, why not? All right, here's our lovely baseball player. There's the bat. When the ball comes, one thing to keep in mind is that you don't hit the ball at ground level. What is it? He strikes the ball, at 1.3 meters above the ground. All right, so he's swinging rather high. So this is your DIY of 1.3 meters. Okay, and the ball travels up, 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 and it clears a very tall wall in the distance. All right, so you know that your delta dx is equal to 130 meters. This wall is also much higher than where you struck the ball at, so this is at 3 meters. And it clears it. Lovely, a home run. And the question is, what was the velocity that the ball was struck at? Okay, a few things to keep in mind is that your delta dy is not 1.3 meters, it is not 3 meters. All right, you need to look for your delta over here. So your delta dy is equal to 3.0 meters, subtract 1.3 meters, which will give you your 1.7 meters in difference. Okay. As for your dx, in fact, yeah, why not? I'll color code it. Okay. Your delta dx is equal to 130 meters. What else do you know? That's about it. Okay. But you do know that your I'll just color code this properly. Your VIY is at your initial velocity that you strike it at. Let me just draw a picture over here. That's your horizontal component. That's your vertical component. And this is your VI. Okay, so your VI in the y dimension is equal to your VI. And that's opposite, so that's VI times sine of theta. Similarly, your Vx is equal to your Vi times, and that's adjacent to theta, so times the cosine of theta. As for your acceleration, well, your Ax, if you really want to write it out, you can. We're assuming that the object does not experience any sort of air friction. So your acceleration in the horizontal dimension is at 0 meters per second squared. Meanwhile, in the y dimension, it is at negative 9.81 meters per second squared. So this is a case where assuming that upwards is positive and forwards is also positive as well. All right, and that's our setup. So with these givens over here, unfortunately you can't completely solve for time in either of the two. So what you're going to do is you're going to create an equation for each of the dimensions, and then you'll equate them together. Okay, so we'll start off with the the x dimension. In the x dimension, the formula is quite clean. Delta dx is equal to vx delta t. What do we know? We know 130 meters is equal to vi times cosine of theta times delta t. And that's it. That's our first equation. Through lots of experience, I know it's a lot easier to solve these problems if you isolate for VI. Okay, if you try isolating for time, it'll be a nightmare, and you'll see what I mean when we get to that point. Okay, so we're going to isolate for VI. So VI is equal to 130 meters divided by cosine of theta times time. Okay, let's rinse and repeat in the y dimension now. So our delta dy is equal to VIY delta t plus 1/2 a delta t squared. Now, about 95% of the time, this formula is a formula you use in the y dimension. It's not always true, but often you'll have enough givens, for example, your dy, your VIY, and your AY, that you can use this formula because you're just solving for time at the end. Okay. Sometimes you're given, properties of it strikes the ground at this angle, then you can't use this formula. You have to use the other one, which is delta dy is equal to VFY delta t subtract 1/2 a delta t squared. All right, so just read the question carefully and you'll figure out which formula is most appropriate for the y dimension. All right, but the x dimension indisputably will be this. It's not going to change. Okay, so now we can sub the values in for this formula here. So 1.7 meters is equal to VI times sine theta, right? Because that's what your VIY is, times delta t plus 1/2 negative 9.81 meters per second squared delta t squared. Okay. Unfortunately, the picture has to go. I should have drawn this picture in the corner. It's okay. I think you guys memorized this by now. The picture, I mean. Okay, so we have our equation 1 and we have our equation 2. So this is equation number 1 and this is equation number 2. And what we're going to do is that we're going to sub equation 1 into equation number 2. Now since this is going to get really, really messy, what I'm going to do is I'm just going to clean things up. I've already shown my units at the beginning, so this time I'm just going to have things cleaned up a bit. So 1.7 is equal to VI times sine theta delta t subtract 4.905 delta t squared. Okay, I've shown my units earlier, so in the intermediate calculations we can drop the units. Yeah, I'll even drop it here as well. Okay, just to keep things quite a bit cleaner. All right, otherwise it just becomes too overwhelming when we deal with everything. Okay, so I'm going to sub 1 into 2. All right. Now let's be careful with our color coding. 1.7 is equal to, and you know what, I forgot to change that to green VI. There you go, okay, because we're going to sub this directly right up into there. Okay, so 1.7 is equal to, okay, let's just be careful with this. This is where most students make a mistake, including me. Okay, 130 is on top, cosine theta delta t is down below. Don't forget about the sine theta and delta t. That was part of the original equation. All right, that's the most common mistake made in the substitution, that you forget to write out the original equation. All right, all the variables and terms that exist in there. Okay, now that we have this all written out, this is actually the easier method. The harder method is isolating for time. Okay, so delta t is equal to 130 over VI times cosine theta. And the reason why this is the harder one is because you need to sub it not only to here, but you also need to sub it into something that's quadratic. And you can imagine the amount of mistakes that you make because you forget to square every single term. All right, so that's why I wouldn't recommend that method. Even though it does work, I wouldn't recommend it for that sake. Okay, but maybe that is the easier way in some of the problems. So use your discretion. Okay, back to this question over here. You'll notice a few things. First off, your delta t's. There's one in the numerator, one in the denominator, so that's one less t to deal with. All right, that cleans it up quite a bit. And some of you guys might know that sine of theta over cosine of theta is also equal to tan of theta. Now you could do that, or actually there is no shorter way. You just got to do that. Okay, so 1.7 is equal to 130 times tan of theta. And in this problem, I guess you could have left it at sine over cosine theta because you already know your theta. You know it's at 45 degrees. But there are some problems that ask you, well, what angle must you strike it at so that you can get your end result? And in that case, you have no choice but to convert sine theta over cosine theta is equal to tan theta. Okay. And yeah, maybe I'll prove it to you afterwards why that's true at the end of the video. Okay, so that subtract 4.905 delta t squared. What did I do wrong here? Nothing. Wait, something's off. No, that's fine. All right, because we are trying to solve for the time here, okay, because that's what we're left with. All right, so let's bring that over. 4.905 delta t squared is equal to 130 times the tan, and since I know it's 45 degrees, I'll just sub that in right now. I could have subbed it in earlier also. Subtract 1.7. Okay, so our delta t squared is equal to 130 times the tan of 45 degrees, subtract 1.7, all divided by 4.905. In fact, I'll just square root right there so I can pull out my handy dandy calculator and go through the math. So root of 130 times the tan of 45, which is equal to 1. So I probably didn't have to insert that term. However, I did make a mistake because I need to double open bracket over here. Okay, that first bracket is for everything under the radical, and this is within the radical, everything in the numerator first, right? So effectively, these are the brackets that I am trying to factor in. Okay, I'm on my calculator. Hopefully I didn't lose my calculator now. Oh. Oh joy. There's the calculator. And I lost the calculator. Okay, let's type it all in again. Okay. Double open bracket, 130 times the tan of 45, which again I could have dropped. Subtract 1.7, close bracket, divided by 4.905, close bracket, is equal to 5.114. Okay, so it took 5 seconds for it to go up and down and clear the wall in the distance. So with what velocity did they strike it at? Well, I could just simply sub this into there, couldn't I? Okay, so we're going to sub delta t back into equation number 1. So our VI is equal to 130 over cosine of 45 degrees times our calculated 5.114 seconds. So 130 divided by cosine of 45, yet divided by again because I didn't put in brackets, 5.114, and we'll get the answer of 35.95 meters per second. And that's our VI. Taking a look at the problem, 2 sig figs are worst case, so our VI is equal to 36 meters per second. And we're done. Right? So that is the initial velocity of the ball. And mind you, it does change because it's going to slow down and speed up again as it goes down. And yeah, when it hits the ground, it'll be at a higher velocity, but when it clears the top of the wall, it's not at that velocity yet. And you can prove it by doing the calculations if you want to. I do have everything all PowerPointed out if you want a clean version to screen capture for any reason. And there you go. Same answer. Okay, how about we go through another crazy challenging problem. Okay, a golf ball is launched in such a way that when you launch the ball, its maximum height works out to the same as its horizontal range. In other words, you're going to get a perfect square out of this. Now, I didn't draw this perfectly, but hope you get the idea. All right, that ball, when it was launched vertically, the vertical height matches up exactly with the horizontal range, and you get a perfect square. All right, so in other words, your delta dx is the same thing as your delta dy. They have the same exact lengths. All right, so what magical angle must you aim at in order to accomplish this crazy feat? Okay, so one thing let's establish is that the height maximum is equal to the horizontal range, that at the maximum height your final velocity goes to 0, and now let's just start calculating things out. Okay, as mentioned before, the generic formula that you use for the horizontal dimension is delta dx is equal to vx delta t, and based upon any given projectile, I'm just going to draw a generic one over here. Okay, that's the VI. Here's my horizontal component, and here's my ever-changing Vy component. That's why I call it VIY, because you have your VIY and you have your VFY. Meanwhile, Vx, it remains the same throughout the entire journey. And by drawing out the projectile at this configuration, there's our theta. Okay, so when we need to solve for our x component, we're going to use cosine. That's why I have cosine over here. And when we're trying to solve for our vertical component, we'll use sine. Okay, so that's our standard formula for the horizontal component. There's nothing else we can do with it. So we go into the vertical dimension, and there are 2 takes on this. All right, the first one is, well, what if we end up throwing it so that it reaches its maximum height? Okay, so we know the maximum height, or a variable for it, and we know the maximum height, the final velocity goes to 0. Okay, so we'll take this kinematic equation, we'll sub in everything that we know. It finally goes to 0. Your VIY is based upon VI times the sine of theta. Don't forget to square it because there's a square up here. You don't forget to carry that through. And we're doing this on any given planet. Now, I could assume Earth, and I could automatically sub in -9.81, but I'll just leave it as AY because you're going to see something really neat afterwards. Okay, so I'm just going to leave these as variables. Sometimes with physics, all you can do is just leave everything as variables and just keep on calculating away until you have a simplified equation, and then you're going to sub that simplified equation into your Excel spreadsheet or whatnot to solve for the rest. All right. In this case over here, we don't need to go through the Excel one because we will get to one definitive answer, okay, not an equation where your input matters or your initial conditions matter. Okay, so we have two equations so far. We'll sub them into each other. How so? I can't remember. What did I do here? I must have isolated for delta H max. Or D, yeah, okay. Because we stated that H max is equal to delta D, so these two are the same. I just simply subbed that into there. That's what I did. Okay, because remember, we're going to have this box-like configuration for this. Maybe I'll just draw right here. Okay, we're going to have a projectile that looks something like that. So it's going to be at a much steeper angle. And yeah, the math will back up that up as well. It's going to be a lot greater than that. It's going to look something like that when we solve our problem. Okay, however, we're still stuck with an equation with a lot of variables, and we can't do anything else with it. So let's go and create yet another equation. And the last equation is the horizontal range. The vertical timing, okay? Because it starts from ground, it goes all the way up, and it lands back at the ground again. And as it accomplishes that, that means that our delta D in the y dimension goes to 0, right? For the full entire path. This first one is just until you reach the max. The second one is for the entire journey, all the way to the top and back down again. Okay, so yes, we're going to start off with our generic equation for our delta dy, which, as I said, most of the time is this: vi delta t squared, delta t plus 1/2 a delta t squared. We're going to replace our vi y with vi, right? Because our vi y is equal to vi times the sine of theta. That's why we have this here. And what can we do here? Our delta dy goes to 0, because again, you're launching it from ground and it's coming back to ground again. And now we have our fourth equation. We can sub in this term right into here now and hope for the best. I'll wipe out all of my scribbles. And at this point over here, we're going to see a few magical things. First off, remember how I said let's not worry about AY right now? And the interesting thing about this is if you take a look at this, yes, there is no AY term here. So we don't need to worry about here. But here we have an AY term, and here we have an AY term. So we divide both sides of the equation by AY. Those AYs will divide each other out. What does that tell us? It doesn't matter which planet you're doing this experiment on. So you could be doing this on Earth, on the Moon, on Mars, or any other planet where gravity is more or less uniform within the first kilometer or so. All right, so that's valid. Another thing is that we see that the first term has a delta t and another delta t, or delta t squared. The second one also has delta t squared. So we could divide everything on both sides by delta t squared. And that will also divide itself out. So what are we left with? Well, a much cleaner formula that looks like this. And with this cleaner formula, we can take this term, bring it over to the left-hand side so it looks something like that. Do the reciprocal of both sides. So you have sine over cosine is equal to 4/1, and sine over cosine has the same meaning as tan. All right, and from here, all you have to do is the inverse tan of 4, and then you can find out the angle of 76 degrees. All right, so it doesn't matter which planet you're doing this on, or no matter how fast or how slow you're doing, because you'll notice that I never gave you the VI. The VI is just mathematically divided itself out. All right, that you'll always have the same outcome. The angle you need to chip it at is at roughly 76 degrees. Before we finish off, I just want to prove one last thing. Maybe I'll just whiteboard this. I don't know if this will work or not. It does not work. All right, which is the final proof. There you go. Final proof of, what is sine of theta over cosine of theta equal to. All right. And to do this, well, we need to go back to good old SOHCAHTOA, right? Sine is when you have opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tan is opposite over adjacent. Okay, and what we're going to do is that we're going to represent this with that. Sine of theta is now represented by the opposite over the hypotenuse divided by cosine, which is your adjacent over your hypotenuse. Okay, so we're just going to do that direct substitution right now. Just going to line up the equal signs so it looks a bit cleaner. Okay, now let's take a look at this. What do we effectively have? Well, we have opposite over hypotenuse divided by adjacent over hypotenuse, or multiplied by the reciprocal of the second fraction. So when we do this reciprocal, we'll have hypotenuse on top and adjacent down below. The two hypotenuses, if that's plural, divide each other out, and we're left with opposite over adjacent. And if you take a look at it, opposite over adjacent has the same meaning as tan of theta. So that's why tan of theta has the same meaning as sine of theta over cosine theta. Hope you learned something new today, and I'll catch you in the next episode. Bye for now.